See, just for the sake of people who are joined late, right? Previous class, what we discussed is, so we are in the 4th chapter, right? So what did we discuss in the previous class? We discussed about the concept of force experienced by a charged particle, which is projected into magnetic, right? And what was the formula? FB came out to be Q into B vector cross B vector. So you can make a note of this point alone. Those who didn't attend the previous class, please make a note of this. Magnetic force is equal to Q into V vector cross B vector, right? So what is that magnetic force? What is this force called as? It's called Lorentz force of magnetism, right? So it's called Lorentz force of magnetism. So we saw special cases. What was that? If you place a charged particle in the presence of magnetic field, right? If you just place it at rest, what is going to be the force experienced by it? It will be 0, right? Why is it coming out to be 0? Because F is equal to QVB sin theta. When V is 0, you are going to substitute it here. Force will be 0. Okay. Next question is, when theta is equal to 0 degree or 180 degree, means the charged particle is having velocity, right? It is having velocity, but the angle at which it is projected is either 0 degree or 180 degree. Then what is going to be the answer? So answer is going to be again 0. But what is the difference between first 0 and second 0? So when we say the charged particle is placed in the magnetic field and the magnetic force is 0, then what can you conclude? The particle still continues to be at rest. Whereas in this case, what will happen? The particle will have a uniform velocity and it will move in a what path? Straight line path. Okay, that is an important point to be noted, right? So I explained about this Lorentz force. When you talk about Lorentz force, F is equal to Q into E vector plus B vector cross B vector, right? Next. So we discussed about Fleming's left-hand rule. What does Fleming's left-hand rule speak about? You take the 3 fingers of your left hand, place them mutually perpendicular to each other in such a way that forefinger represents the direction of field, central finger represents the direction of current, and thumb represents the direction of thrust, which is the force. So just to understand, if B vector is like this, B vector is like this, Fleming's left-hand rule mainly speaks about right ladder left. Now, Fleming's left-hand rule mainly speaks about how much is the force experienced by a current carrying conductor placed in magnetic field. So when I talk about a current carrying conductor, you can talk about a charged particle also. So if I say current, the central finger shows the direction of current, right? If suppose instead of current carrying conductor, had they given you charged particle, what should be the direction of charged particle for it to be in the direction of current? The charged particle should be positive. For Fleming's left-hand rule, central finger represents the direction of current. But till now, we didn't discuss about current. We discussed only about charged particle. So when I say charged particle, what should be the charged particle? The direction in which the positive charge is moving will be assumed to be the direction of current as well, because current is from higher to lower potential. Okay. So having said that, let's say there is a scenario where velocity vector is upward, magnetic field is in this direction. Then how are we going to apply the Fleming's left-hand rule? So don't extend all the 3 at the same time. So go one by one. Always, whenever you're asked to find the final value, 2 parameters will be known to you. Depending on the 2 parameters that you know, first open those fingers. In this case, I know the magnetic field. So I'll open my forefinger. So forefinger is placed in the direction of field. So central finger is opened. It is placed in the direction of current. Is it placed? Check my finger. Is it placed in the direction of current? No. So what am I supposed to do? Tilt it anti-clockwise so that this becomes the direction of the current. So extend your thumb. The thumb gives you the direction of force. Means this charged particle is experiencing a force into the plane. Are you able to understand this point? Right. So that is why I put an into mark here. Okay. Next is, yeah. Motion of a charged particle in uniform magnetic field. Again, when the initial velocity is parallel to the magnetic field, that is theta is equal to 0 degree, then what will be the force experienced by it? 0, and the particle continues to move in a straight line. This I've already given, right? And the most important concept that we discussed in the previous classes, motion of a charged particle in uniform magnetic field when the initial velocity is perpendicular to the magnetic field. When initial velocity and magnetic field are perpendicular to each other, then what is going to be the path of the charged particle? It will be circular. And what is the name of the motion? It will be a uniform circular motion. For uniform circular motion, what is most important? What force is important? Centripetal force. So centripetal force formula is mv square by r. Who's providing the necessary centripetal force? It is the magnetic force. So basically the derivation is only 2 steps, right? So force experienced by the charged particle in the presence of magnetic field is QAB. Centripetal forces mv square by r. Equate both. On equating both, what are you going to get? R will be equal to mv divided by qb. Mv can also be written as p, which is the linear momentum, and it can also be written as root of 2m into k divided by qb. Are you able to understand this? Right? Similarly, when we calculate the time period, when you talk about the time period of revolution, time period is equal to total distance traveled by speed. In one revolution, how much is the distance it is going to cover? You cover a distance of 2 pi r divided by what is the speed with which it is moving? It is v. So in the place of r, you will substitute mv by qb. V and v will get cancelled. So what is the important conclusion we drew out of it? Time period does not depend on the initial velocity of the particle. You project it with whatever velocity you want. If the particle is still the same, if the magnetic field is still the same, it will complete the circular path in the same amount of time. Meaning, if you project a particle with 1 meter per second, let's say you take an electron, you are projecting in a magnetic field B. If you project that electron with 1 meter per second or 10 meter per second, it will complete the circular path in the same amount of time. Okay. Now, what is going to be the frequency? So frequency is the reciprocal of time period, which is going to be qb divided by 2 pi m, and the name of this frequency is called as cyclotron frequency. Okay. So about this, the detailed videos are already put in the app where we have cut it into each parts. Okay. So if you want to know about each subtopic, it is already there. I hope you guys have opened the app and seen, right? It is broken into 3 parts. What are they? Live recordings, pre-recorded, and paper discussion. Okay. In the live class recording itself, we have broken it into chunks. So you can always have a look at it whenever you have it. That point clear? So next, we are going to get started with the next important topic. Let's observe what it is. Okay. So next topic is So next topic is motion of a charged particle in a uniform magnetic field when the initial velocity makes an arbitrary angle with the field direction. So when I say arbitrary angle, here the angle theta is going to be anything other than 0, 90 degrees or 180 degrees. Okay. Let's say there is a uniform magnetic field existing in the horizontal direction, where I'll call the uniform magnetic field as B. Okay. Listen to this very carefully. If I take a charged particle direction. If I take a charged particle and project it with speed v at an angle theta with respect to the magnetic field, then this v can be resolved into two components. What are they? So v can be resolved into two components, which is going to be v cos theta and v sin theta. Now, if you observe, v cos theta is a component which is parallel to the magnetic field, right? And v sin theta is a component which is perpendicular to the magnetic field. Now, what we are going to do is combine the knowledge from the previous two scenarios and write an answer to this. Observe. So v cos theta being the parallel component, so it is the parallel component. What will it try to do? When the charged particle was projected parallel to the magnetic field, but the charged particle was projected parallel to the magnetic field, what was the path taken by the particle? It is going to be a straight line, meaning this v cos theta is going to put the charged particle in a straight line path. Okay, so what will happen here? It is going to be a straight line. So v cos theta is going to put the particle into a straight line path. Then v sin theta is there. What about v sin theta? So v sin theta is going to be the perpendicular component, right? It is going to be the perpendicular component. So what happened in the case where you have the velocity perpendicular to the magnetic field? The particle was put into circular motion, right? So what will happen here? The particle will travel in a circular path. Is the point clear? Right. First, make a note of this. Right? So v cos theta will put the particle in a straight line path and v sin theta will put it in a circular path. Now observe, when this is putting the charged particle into circular path, what is going to be the direction in which it will experience the force? What is going to be the direction in which the charged particle will experience the force, and how is it going to move? So due to this v sin theta, use the Fleming's left-hand rule and tell me what is going to be the direction in which this v sin theta is going to create a force on the charged particle. So you take forefinger, apply it in the direction of field. Central finger in the direction of current. If I take this to be a positively charged particle Q, then it is going to be in the direction of current, and when you extend the thumb, it is going to be into the plane. So what will happen here is this v sin theta is going to put the charged particle into circular path into the plane. So what will happen is, if you see from this side, right? If you see from this side, the charged particle will go in a circular path like this. What will happen? It will go in a circular path. So when I see it from here, it is going to be in a circular path in which direction? This side. Like this. It is going to be in the anti-clockwise direction. Right? So what is going to be the radius of the circular path which is going to take place? So for radius of circular path, we need not apply any formula. We need not derive anything. We already have a ready-made formula. What is it? R is equal to mv divided by qb. So here, when I talk about v, camera charge. So when I talk about V, here it is a perpendicular component which is actually responsible for the circular path. So what I will write here is M into, what should I write in the place of V? I'll write it as V sine theta the whole divided by Q into V. Are you able to understand this scenario? So it is going to be V sine theta divided by Q. Okay. So this is going to be the radius of the circular path. Now I want you all to concentrate. See, due to the perpendicular component, it is the circular path accepted. But due to the parallel component, that is V cos theta, it is going to be in a straight line path. So it will neither be able to complete a full circle or neither it will be able to completely move in a straight line path. So what is going to happen in this scenario? There will be a path that will get created like this. So there will be a spiral path created because it is a combined motion of circular and translation. So if the particle starts here, observe, if the particle starts here, by the time it is coming back to the same point, it is already pushed in this direction. It is pushed in this direction due to whom? Due to V cos theta. So it will be a combined circular and translational motion. Hence, this kind of a path will get created, which is called as the helical path. What is it called? It's called as the helical path. And this distance is there, right? This horizontal distance that is going to exist. So this horizontal distance that is existing between two complete rotations. Okay, I'll take it like this. Correction here. I can say the horizontal distance traveled by the particle in one complete rotation is called as pitch. So what is it called as? Pitch. So horizontal distance traveled by the particle in one complete revolution. Okay. Shall I proceed? Okay. Listen. Now, we need to calculate what is the pitch of this helical motion. Right. So pitch is what? It is the horizontal distance covered by the particle. It is a horizontal distance covered by the particle in one complete revolution. Right. So what can you write pitch as? Pitch is the distance. So what is the formula for distance? Distance is equal to speed into time. So how much? What is the speed that is contributing to the pitch? Which component among both is contributing to the pitch? It is V cos theta. Right? It is going to be V cos theta multiplied with how much time is it taking to complete that revolution? It is taking a time of one complete revolution is completed in how much time? One time period into capital T. So it is going to be V cos theta multiplied with what is going to be the time period. If you look at the formula, time period is 2 pi m divided by QB. So when you multiply these two, you will get the answer as 2 pi mv cos theta the whole divided by QB. So 2 pi mv cos theta the whole divided by QB is what is going to be the pitch. Is the point clear? So these two expressions are to be remembered. Radius of the circular path is mv sin theta divided by QB. And what is going to be the pitch? It is 2 pi mv cos theta divided by QB. Q into beta. Done copying? So now we'll discuss the next topic, that is force experienced by current carrying conductor placed in magnetic. So till now, all that we discussed is what happens when a charged particle is projected into the magnetic field. Now what we are going to see is what is going to be the force experienced by a current carrying conductor placed in magnetic field. Okay. Suppose I have a magnetic field existing into the plane. Okay. In which there is a current carrying conductor placed like this. Now, when I talk about a current carrying conductor, what is going to be present inside it? There is going to be charged particles, right? Basically, they are electrons. And how are these electrons going to travel? If at all, I say that the current is flowing in this direction, if I say that the current is flowing in this direction, what is going to be the direction in which the electrons will move? They'll be in the opposite direction. So it is going to be VD. So what is that VD? It's called as the drift velocity. This we already know. Suppose I take the length of the conductor to be L. I take the length of the conductor to be L and the magnetic field to be D. Okay. Now what I'm going to tell is, let the number of charged particles inside the conductor B capital N. So let the number of charged particles inside the conductor be capital N. Okay. And what is going to be the charge of each electron? So charge of each electron be A itself. Okay. Now listen to this carefully. If I take one electron, how many? I'm taking one electron and I'm observing what is going to be the force experienced by that one electron because of its speed. See, what is the name of the topic? We are seeing force experienced by a current carrying conductor placed in magnetic field. Now tell me one thing. When I think of current carrying conductor, what comes to your mind first of all? What is there inside a current carrying conductor? Charged particles which are moving. So when a charged particle is moving in the presence of an in the presence of a magnetic field, what will happen to it? It will experience a force, right? What is going to be the force experienced by that one electron which is under observation? Fp is equal to minus E. See, basically, magnetic force is equal to Q into V vector cross B vector. So it is going to be minus E into, what can I write V vector as? Can I write it as BD vector cross? I'll write it as B vector itself because I'm not concerned about the orientation. Is this point getting registered? Is this clear? Now, the next question is, since I have drift velocity, is there a possibility for me to write drift velocity in terms of distance and time? Is there a possibility for us to write drift velocity in terms of distance and time? How will you write it? So speed is equal to distance by time. Okay. So can I write this as minus E into, observe this, minus E into drift velocity, can I write it as L vector divided by T? Can I write it like this? L vector divided by T cross B vector. Makes sense? So this is the force experienced by whom? This is the force experienced by one electron. Force experienced by one electron. So if I want the force experienced by n electrons, what are we supposed to do? If I need the force experienced by n electrons, Fb will be equal to minus Ne into L vector divided by T cross B vector. Make sense? So if I take the T outside, right, if I take that T outside, minus Ne divided by T into, can I write this as L vector cross B vector? So minus Ne is going to be the total charge. So total charge per time taken is what is called as current. So Ne is total charge due to what? Quantization of charge. So total charge divided by time taken is going to give me current. So can I write this as I into L vector cross B vector? Right? It is going to be I into L vector cross B vector. And this is going to be the force experienced when you place a current carrying conductor of length L in a magnetic field B. Okay. So you can make a note of this. Is that point clear? So this force I into L cross B can also be written as, so FB vector is equal to I into L vector cross B vector can also be written as ILB sin theta, where theta is going to be the angle between L vector and B vector. So for L vector, what you do is, for L vector, we give the direction of current itself. So for L vector, we give the direction of current itself. Is the point clear? So it is going to be ILB sin theta, or some books write it as BIL sin theta. Right? So if I write it in the form of vector form, listen to this carefully. ILB sin theta, you can put an n cap, where n cap will be perpendicular to both L vector and B vector. It will be perpendicular to both L vector and B vector. If you write it only in terms of magnitude, FB will be equal to I into L into B sin theta. Right? This is something that you need to remember. L vector is the direction of current itself. Done? So let me go to the next topic. You can write down the heading: torque experienced by current carrying loop. Right. Yes. So the next topic is going to be torque experienced by a current carrying loop placed in magnetic field. So this is also another important topic. So with this concept only, we'll understand about some measuring instruments like ammeter and voltmeter, also a sensitive instrument called as galvanometer. You've heard all these terms, no? So we'll be learning about all those things on how they are working. For that, the answer is going to be torque experienced when you place a current carrying loop in the magnetic field. Okay. So observe this. If I take a region of magnetic field, in that region, let's say we are placing a conductor like this. And in this conductor, which is basically in the form of a loop, right? This conductor is closed, unlike the previous one. So in the previous case, what did we see? We saw that the conductor was open. There, whenever the conductor is open, it will experience force. Whenever the conductor is closed in the form of a loop, it will experience torque. So why is it experiencing? Let's see. So if I take this to be I, the current is going to flow in the closed loop like this. Okay. Let's say the length of this portion is going to be A and this is going to be B. Is it clear till this step? Okay. I've considered basically only one loop. Now observe. This loop, can I say, is formed due to the combination of So can I say that this loop is basically formed as a combination of 4 conductors, right? So of which, if I take this to be the first conductor, this is second, this is third, and this is fourth. Okay. So if I take them in this order, then what is going to be the force experienced by the first conductor? What is going to be the force experienced by the first conductor? So force experienced by the first conductor is I into length of the first conductor, or I1 into L1 into B. Right. What is the value of I1? It is I only. What is the length of the first conductor? A. So what is going to be the magnetic field? It will be capital B. Is the point clear? So it is going to be IAB. Similarly, what is going to be the force experienced by the second conductor? What is the force experienced by the second conductor? I2 into L2 into B. See, here I want to make a clarification. See, I wrote it as I1 L1B. It is going to be sine theta also. So what is the angle between the length of the conductor and magnetic field? How much? 90. That is why I wrote it as I1 L1 B. I1 is I, L1 is A into B. So what about the second case? I2 into L2 into B sine of theta. So angle is going to be, this is the direction of current, this is the direction of magnetic field. Angle between them is 0. So since it is 0, force experienced by the second conductor will be 0. So what about the force experienced by the third conductor? I3 into L3 into B into sine theta. What is it going to be? It is I into this distance is going to be A into capital B sine of 90 again. Because this is the direction of current, this is the direction of magnetic field. So it is going to be IAB. Then what about the force experienced by the fourth conductor? Fourth conductor will be 0 again, because the angle between the L vector and B vector is 180. Right? It is going to be 0. Now, if you observe, F1 and F3 come out to be the same values. But the question is, what is the direction? What is the direction in which the force is going to act on the first particle? Sorry, first conductor. Apply the Fleming's left-hand rule and tell me the answer. Field, direction of current, thumb. So the first conductor is experiencing a force into the plane. So what about the second conductor? Field, central finger, thumb. It is experiencing a force outward. So what is happening here is, here the force is into the plane, here the force is out of the plane. The other two conductors are experiencing no force itself. So what is the total force experienced by the loop as a whole? What is the total force experienced by the loop as a whole? So F1 plus F3 in the vector form, when you add it, one force is into the plane, the other force is out of the plane. The answer will be 0. So the net force experienced in this scenario is going to be 0. Right? The net force is going to be 0. That is why if you see the topic, it is not speaking about net force, rather it is speaking about the net torque. Meaning what will happen to this kind of a loop is, it will not have any translatory motion, but it will have a rotational motion. Why? We will see. Let me know once you're done. You're done with this? Now if you observe, if I take an imaginary line like this, if I take this to be the axis, right? How much is this distance? This is b by 2, this is b by 2. Right? Now if you observe, force is coming in this direction, right? For the first conductor, force is in this direction. And from here till the axis of rotation, the distance is going to be b by 2. Okay. Now, let us try to calculate what is the torque experienced by it. What is the torque experienced by the first conductor? So if I take torque 1, can I write it as r vector cross f vector? So torque experienced by the first particle, can I write it as r vector cross f vector? So r vector, if you see, it is going to be from the current carrying conductor towards the point. So it is going to be b by 2 I cap cross, what is going to be f vector? F vector is going to be IAB minus k cap. Okay. So answer will be, sorry, there's capital. Answer will be IAB into capital B divided by 2 into I cap cross minus k cap. So what is I cross k? So if I take the circle, this is I, J, K. What is I cross k? I cross k is minus j, minus of minus j will be plus j. So I into this AB is going to be capital A into B divided by 2 multiplied with I cross k is minus j. So it is going to be j cap. Listen to this carefully. So what is the meaning of this is, A into B is going to be the area of this loop because it's taking the shape of a rectangle. Right. So that is why I replaced it with capital A. Right. This is going to be the value of torque experienced by the first conductor. Similarly, if I want to calculate what is the torque experienced by the second conductor, what is the answer going to be? Torque experienced by the second conductor is 0. Same is going to be the torque experienced by the fourth conductor. Am I right? then what is going to be the torque experienced by the third conductor? So what is the torque experience? So torque experienced by the third conductor, if it is going to be minus j cap, then when I add both, how much will the answer come out to be? Then why are we discussing this topic? There should be a non-zero torque, no? So that's where the tricky part is. Listen to this. So here it is going to be r vector cross f vector. Observe how I'm writing this r vector as r vector is b by 2 times minus I cap. So b by 2 times minus I cap cross what is going to be the force vector. So when I talk about the force vector, force is coming out. So what is the magnitude of force? IAB, and what is the direction? K cap. So it is going to be IAB in the direction of K cap. So what is going to be the answer? It will be I into AB into capital B divided by 2 into minus I cross K is also going to give you J cap. Observe I cross minus K and minus I cross K, they both are same. So it is going to give you J cap. So this is going to give you IAB the whole divided by 2 times J cap. So where capital A is nothing but the area of this rectangular portion. So what is going to be the net torque experienced by the system? So net torque experienced by the system will be equal to torque experienced by 1 plus torque experienced by 2. So what is going to be the answer? It will be I into A into B times J cap. Okay. So the net torque experience is going to be I into A into B, but don't memorize the J cap because J cap is specific to this particular derivation. Okay. So if I write it only in terms of magnitude, the net torque experienced by the system is going to be I into capital A into B. And remember, I into A into B is happening only for one loop. If there are n turns, then the net torque is going to be NIAB sin theta. It is going to be NIAB sin theta. Okay. So basically it will be NIAB and you add a sin theta to it because when you do this R cross F and all, you will have that sin theta component. Okay. So this is going to be the net torque experienced. Okay. A into beta. A into B is the rectangle, no, area of the rectangle. Capital A is the area of the rectangle. I cross minus. You know that circle, right? For that circle, what you're supposed to do is take IJK in the anti-clockwise direction. Okay. After you take it in the anti-clockwise direction, what you do is, if you take I cross J, see anything in the anti-clockwise direction is positive. So I cross J is K, J cross K is I, K cross I is J. Anything in the clockwise direction is going to be negative. Understood? So I cross K will be clockwise. I cross K is minus J. So I cross K is minus J, minus of minus J will be plus J. That's the answer. Okay. So this is also a very, very, very important result based on which the next set of our discussion will be. So I'll be using this as a first term to derive something tomorrow. So remember these expressions for next class. The point here. Right. So any other questions?
No, sir.
There are no questions, we can wind up.
Thank you, sir.
Yeah. Those are online?
Sir,
Yeah, we can wind up.
okay, sir. Thank you, sir.